watching session number 2 of the chapter Biomolecules. In the previous session, I talked about carbohydrates, in particular the classification of carbohydrates, preparation of glucose, elucidating the structure of glucose. In this session, I am going to continue with some other concepts related to carbohydrates. We came to know how glucose can be prepared from sucrose as well as starch, and we came to know that what are the main reactions involved with glucose and the conclusion drawn from the respective reactions also we have seen. So now we'll see how actually the glucose structure is. Fischer is a scientist, and he gave the open chain structure of glucose, and we call it as Fischer's structure of glucose. So now I am going to explain the Fischer structure of glucose. So let me write here Fischer's structure of glucose. So first we will see what is the main molecular formula what we know, that is C6H12O6 is the molecular formula of glucose, we know that. And while explaining the concepts of elucidating the structure of glucose, I have written one simplified form of the structure of glucose, and that is CHO at the top, in the middle CHOH, we have 4 times of that CHOH, and below we need to write CH2OH, and this is one simplified structure, and using this structure we have written the reactions of glucose, as you know. So this is the known concept of structure of glucose, and now we'll see what is actually the Fischer's open chain structure of glucose. So Fischer's open chain structure of glucose I am going to draw here. So just see how I am going to draw the Fischer structure of glucose. So from these two the concepts, we know that one the glucose has 6 carbons and 12 hydrogens and 6 oxygen. And if you just recall the elucidating structure of glucose, and we came to know that the glucose contains 6 carbon atoms in a straight chain, isn't it? So what is the experimental proof for that one? And we know that when glucose is heated in the presence of hydrogen iodide and red phosphorus, we get N-hexane as the product. So because of this reaction, the product we got N-hexane, therefore we can say that the glucose contains 6 carbon atoms in a straight chain. That is the conclusion drawn from the reaction that I discussed. So now I am going to draw the 6 carbon atoms in a straight chain. So see here 1, 2, 3, 4, 5, 6. So 6 carbons I have drawn. So you need to give the numbers for that one. So this is carbon number 1, okay, and this is 2, 3rd carbon, 4th carbon, 5th carbon, and 6th carbon. We know that one 6 carbon atoms are in straight chain, and at the top we have CHO, that is functional group aldehyde. So I can draw like this, C double bond O and C single bond H, that is nothing but the functional group aldehyde, isn't it? And bottom what we have, CH2OH we have, I am going to write here CH2OH, right? So in between we have 4 carbons, 1, 2, 3, 4, and 4 carbons we have, and the arrangement is a CHOH, means we have hydrogen as well as the OH group also, 4 we have here. So what the Fischer's rule says that you have to see the carbon number 3, carbon number 1, carbon number 2, carbon number 3, and on carbon number 3 hydrogen is on right side and OH is on left side. This is very important, you need to know. I repeat, in Fischer structure carbon number 3 hydrogen is on right side and OH is on left side. And what about carbon number 2, 4, 5? That is exactly opposite of the configuration at C3. So hydrogen we have right side. So here I should write OH okay, opposite of that one, and here also OH and here also OH here. So just try to observe on carbon number 3 only hydrogen is on right side, whereas the remaining we have OH, and if we write OH and opposite will be exactly H, okay, and here we have H again on carbon number 4 and carbon number 5 also we have H, and that is actually the Fischer structure of glucose. Remember, Fischer structure of glucose is nothing but the open chain structure of glucose. We draw Fischer structure means that is always open chain only, and this is actually how does glucose molecule C6H12O6 looks like. Okay, so this is the way how you are supposed to remember that one. So first you need to write 6 carbon atoms in a straight chain, right, and you need to give the numbers. At the top we have CHO, at the bottom we have CH2H, right. On carbon number 3, H is on right, OH is on left side, and remaining is exactly opposite configuration of that. Okay, so that is actually the Fischer structure of glucose. So this is the complete open chain structure. Sometimes we may write the same structure in one more form also. So what is that one more form? I am going to explain here. So we have this kind of structure. So I am going to draw a straight line. Okay, so 1, 2, 3, and we have one more 4. Okay, and these are nothing but the bonds which are present, and this is carbon number 1, carbon number 2, carbon number 3, 4, 5 and 6. Okay, first carbon, so at the top what we have? CHO, we should write CHO here. At the bottom we have CH2OH. I am going to write here. So for your reference I may number this one 1, 2, 3, 4, 5 and 6. On carbon number 3, H is on right side and OH is on left side, and remaining will be the opposite configuration of that. So OH on the right side, H on the left side, OH on the right side and H on the left side, and this is also the Fischer open chain structure of glucose. So try to know that one. So you can represent like this also and you can represent like this also. Okay, so both are the Fischer chain structure of glucose itself. So now this is the structure, and we know some concepts by observing the elucidating structure of glucose, and now we will finalize in general what actually the glucose consists of. So we will write one by one. I am going to write here what actually the glucose consists of. So now if you observe the Fischer structure of glucose, so one can say that 6 carbon atoms are there and they are in this straight chain here. So the first conclusion is 6 carbon atoms. 6 carbon atoms in straight chain. So this is the first conclusion what I can write. The second one is, if you observe carbon number 1, we have a functional group, okay, and that particular functional group is aldehyde. So just recall the elucidating structure of glucose. When glucose reacts with hydroxylamine, we will get oxime of glucose, isn't it? Similarly, when glucose reacts with the hydrogen cyanide, we will get a cyanohydrin of glucose. So based on these two reactions, so what is the conclusion we have drawn? The conclusion is glucose contains carbonyl group, isn't it? So therefore, what I am going to write here is carbonyl group is present in glucose. We have seen the reaction that already. Similarly, one more point I am going to write here, that is functional group present in glucose is aldehyde. Here you can see, here is the position of the functional group, that is aldehyde, and then see how we came to know that the glucose contains aldehyde. So just to recall the reaction what I explained, when glucose reacts with the bromine water, bromine water is the oxidizing agent, therefore when glucose reacts with bromine water, we are going to get a gluconic acid. Aldehyde group is converted into carboxylic acid group. So based on this reaction, the conclusion what we have drawn is glucose contains aldehyde functional group. So the functional group present in glucose is aldehyde, right? Now one more concept I am going to explain here. So now we will see how many asymmetric carbons are there. How many asymmetric carbons are present in a glucose? Okay, remember asymmetric carbon, the carbon which is joined to 4 different atoms or groups, we call it as asymmetric carbon. And remember, asymmetric carbon can be represented by a symbol, and that we call it as asterisk. In simple language, star I can say. So that is how actually asymmetric carbon is going to be represented. Remember, in a compound, if you are going to get asymmetric carbon and that has the property, we call it as optical property. So now we'll see how many asymmetric carbons are present in a glucose. So we know that 6 carbon atoms are there. So out of 6, how many asymmetric carbons are there? I am going to explain now. So now if you consider carbon number 1, and here we have H and here we have double bond O, and this is one more group here. So we don't have 4 different atoms or group, we have only 3, isn't it? So therefore I am going to say this is not asymmetric carbon. The carbon number 2, if you observe, so just concentrate on carbon number 2 only. This is one group, hydrogen is one, OH is one, and remaining is one. So 4 different groups we have. Therefore this carbon is asymmetric carbon. I am going to represent it by asterisk. We call it as star. Okay, so carbon number 2 is asymmetric carbon. What about carbon number 3? This is one asymmetric carbon. OH is one group, H is one group, and this is one group. Therefore carbon number 3 is also asymmetric carbon. And now you just guess what about carbon number 4? Is that asymmetric carbon or not? H is one, OH is one, above we have one group and below we have one group. All are completely different. Therefore carbon number 4 is also asymmetric carbon. What about carbon number 5? H we have, OH we have, below we have CH2H, and above we have this group. All are completely different. That is also asymmetric carbon. What about carbon number 6? We have this group, we have OH, and CH2 I can write, H I can write here, H I can write here. So 2 identical, 2 same groups I have. Therefore carbon number 6 is not asymmetric carbon. Right. So what is our final conclusion regarding asymmetric carbon? In glucose we have 4 asymmetric carbon. And what are those carbons? Carbon number 2, 3, 4 and 5. So now I am going to say that in glucose we have 4 asymmetric carbons. So carbon which is attached to 4 different atoms or groups, that we call it as asymmetric carbon. And since glucose has asymmetric carbon, and one can easily say that glucose has the property of optical activity. Okay. Now we'll see how many OH groups we have here. How many OH groups? So we discussed one reaction, that is when glucose undergoes reaction, that is nothing but acetylation. When glucose reacts with acetic acid, we get glucose pentaacetate, and that represents glucose has 5 OH groups. So glucose has 5 OH groups here. That is the experimental proof. Just to see 1, 2, 3, 4, 5. 5 OH groups we have, and that is the one more concept related to glucose. And 5 OH groups we have, and OH, all the OH are attached with the carbon, and that we call it as alcoholic kind of functional group. And now we'll see out of 5 OH which one is primary alcohol and which one is secondary alcohol. So now you just observe the last one, that is CH2OH, and I am going to say that one, the CH2OH is primary alcohol. This is primary alcohol, and we have seen the reaction of that also. When glucose and gluconic acid reacts with the concentrated HNO3, which acts as strong oxidizing agent, and we are going to get saccharic acid. So based on this reaction we can say that the glucose contains 1 primary alcohol. So in glucose we are going to get 1 primary alcoholic functional group we have, and remaining is 4. Okay, so 4 secondary alcoholic functional groups we are going to see. So this is the primary alcohol, whereas 1, 2, 3 and 4, and these are the secondary alcohol what we are going to see. So these are the conclusions what I am discussing here, and the reactions I discussed that already. So now we know that one, that is if any compound has asymmetric carbon, that shows the property of chirality and optical isomers. So we are going to get optical activity is the property related to that. So now we'll see when glucose we have and we have asymmetric carbon, how many optical isomers are possible for this one. So optical isomers, how many optical isomers are possible for this glucose, and we have one formula to calculate that, and the formula is 2 raised to n, where n stands for number of asymmetric carbons I repeat, N stands for number of asymmetric carbons. So how many asymmetric carbons are there in glucose? We know that one in glucose we have 4 asymmetric carbon, that is represented by asterisk or star here. So 4 we have in the place of N, I am going to write 4, 2 to the power 4, we are going to get what actually, that is 16. So glucose has 16 optical isomers. So 16 different structures we can draw, and that shows the property of optical activity. Optical isomers for glucose is 16. This is what actually the glucose contains. After knowing the different constituents of glucose structure, we will discuss one nomenclature of the configuration, and that we call it as D and L configuration. D and L configuration. So we'll see now what actually D configuration and one more is L configuration. I am going to consider one very simple example. So just see, let me draw the structure of the example what I am going to consider. CHO at the top, in the middle C and OH on the right side, H on the left side, and at the bottom CH2OH. One more identical structure I am going to consider here, CHO, C, H on the right side, OH on the left side, and at the bottom CH2OH. So the name of these two compounds, let me write here, this is glyceraldehyde, and this compound is also glyceraldehyde. We'll see what is the change in configuration we are going to observe. So just you look over these two structures, and one can easily say that there is a change we are going to observe in carbon number 2. The configuration at carbon number 2, or I can say the arrangement of different atoms on carbon number 2 is different. What is the difference? On carbon number 2 we have OH on the right side and H on the left side. On carbon number 2 of this one we have H on the right side and OH on the left side. So this is the two different forms of glyceraldehyde what I consider as an example. So now if you want to name these compounds as D and L configuration, first you are going to see whether the given compound has asymmetric carbon or not. So now if you consider this one, and now I hope you can easily guess that this carbon is asymmetric carbon, carbon number 2, because this carbon has been attached with 4 different groups, therefore that is asymmetric carbon. Similarly in this structure, second carbon is the asymmetric carbon. So first step is you have to identify the asymmetric carbon, and after identification the asymmetric carbon, the rule says that on the asymmetric carbon, if OH group is on right hand side, and that we call it as the D configuration. Therefore this compound I call it as the D-glyceraldehyde. Why D-glyceraldehyde? Because on asymmetric carbon OH is on right hand side. If on asymmetric carbon OH is on left hand side, and that we call it as L configuration, and this compound I name it as L-glyceraldehyde. So now D and L, that depends on the position of OH groups on asymmetric carbon. On asymmetric carbon OH group is on right side, D configuration. On asymmetric carbon OH is on left side, we call it as L configuration. This is how we can name the given compound with asymmetric carbon as a D and L configuration. One more part I am going to explain in the same structure, and that is what is actually the meaning of plus. Actually this structure is plus glyceraldehyde and this structure is minus glyceraldehyde. So what is this plus and minus stands for, and what this represents? Let me consider one mirror plane in between these two. So just observe, you are supposed to place a mirror in between these two. So this is a mirror, if you assume that. And if you consider a mirror in between these two compounds, and now you can easily guess, CHO is exactly the mirror image of this CH, isn't it? And OH is the mirror image of this OH, and H is also the mirror image of this H, and CH2H is the mirror image of CH2H. So all groups are mirror images to each other. So I am going to say these two are mirror image isomers. Since we have asymmetric carbon, that shows optical activity property, therefore I can better say optically active mirror image isomers, isn't it? And now we will check whether it is going to be superimposed or not. And what for that one we can represent in very simple manner. So just see, let us assume my left hand is D plus glyceraldehyde and the left thumb represents the OH. And if I consider right hand as L minus glyceraldehyde and the thumb of right hand is this OH, so I am going to lift this and I am going to place over here, and if I place this over here and the OH of the left one is completely different from OH of the right one because they are not going to be placed on the same, isn't it? So that we call it as non-superimposable. So if I just remove this and if I place over here, OH you are going to get here and H you are going to get here. Okay, so that is not as it is, superimposable. They are non-superimposable. So non-superimposable, optically active mirror image isomers, we have one word and that we call it as enantiomers. So these two I can say enantiomers. Why? Because these two compounds are non-superimposable and these two compounds are optically active and these two compounds are mirror images to each other and shows the property of optical activity, and therefore these are enantiomers. And remember, when you consider a compound or you can say a chiral compound, and if it has the property of rotating the plane polarized light, we know that one. If any compound rotates the plane polarized light towards right side, and that is represented by plus. This plus represents the compound rotates plane polarized light towards right side. And if compound rotates the plane polarized light towards left side, and then we write what is that, a minus here. So try to know plus and minus depends on the ability of a compound to rotate a plane polarized light either towards right side or towards left side. Remember, plus right side and minus left side, and the compound should have the asymmetric carbon. And D and L is not at all related with the plus and minus. Know this concept. D and L, capital D and L, that is not related with plus or minus. I told you already. D and L. D stands for on asymmetric carbon, OH is on right. L stands for on asymmetric carbon, OH is on left. Plus stands for the compound rotates plane polarized light towards right. And minus represents the compound rotates plane polarized towards left. One more thing you try to know, plus and minus are experimental quantity. If I give you or if I draw the structure of any optical active compound and if I ask you whether it is plus or minus, or you can say dextrorotatory or levorotatory, small d small l we write here, that is small d small l, and here plus and minus we have, and we cannot say that one because that is the experimental quantity, whereas the D and L, and we can say by the position of OH on the asymmetric carbon in the structure itself here. So now this compound I say it as D plus glyceraldehyde, and this compound I say it as L minus glyceraldehyde, and that is actually the concept of DL configuration. And try to know that one on asymmetric carbon. This is the very important thing. You need to know, you need to check the asymmetric carbon. On asymmetric carbon, if OH group is on right hand side and that configuration is D. On asymmetric carbon, OH group is on left hand side and that configuration we call it as L. And remember, you have to check asymmetric carbon, then we are going to get whether it is D configuration or L configuration. This is the explanation of D and L configuration by considering the example that is glyceraldehyde. Now We know the structure of glucose. We know the open chain structure or Fischer structure of glucose, and now my question is this, the name I have written glucose, and whether this is D-glucose or L-glucose, you need to check it out. Whether the glucose is D-glucose or L-glucose. And the first step I told you, you need to identify the asymmetric carbon. We know that one, these four are the asymmetric carbon. And then one question arises. What is that? In glyceraldehyde, we had only one asymmetric carbon, and based on that we identified the position of OH. Right side L, right side D, left side L. But here we have four asymmetric carbon, and which asymmetric carbon you need to consider? This is the question arises in your mind, isn't it? So we have one addition rule for that one. If you have one asymmetric carbon, this is the rule what you need to follow. And if you have more than one asymmetric carbon, and in that case you should consider such asymmetric carbon which is far away from the functional group, which is at most distance for the functional group. See here, in this glucose the functional group is aldehyde. Okay, so with respect to aldehyde functional group, which asymmetric carbon is far away or at most distance? And this asymmetric carbon is at the most distance here, and therefore carbon number 5 you need to consider. So carbon number 5 you need to consider. So this is the one addition rule you need to see. Let me repeat that. If we have more than one asymmetric carbon, consider a asymmetric carbon which is at most distance or far away from the functional group. In the structure of glucose, carbon number 5 is the asymmetric carbon which is at most distance from the functional group, that is aldehyde. So now on this asymmetric carbon, if you observe that OH is on the right hand side. Okay, so we know that one, if OH is on right hand side of the asymmetric carbon, and then we represent it as D, therefore glucose is D-glucose. Know that one. So now I can say glucose is actually D-glucose. Why it is D? Because on carbon number 5 or asymmetric carbon which is far away from the functional group, on that we have OH is on right hand side, and therefore this I name it as D here. So similarly, if you get any kind of a structure, and first you need to observe the asymmetric carbon, and based on that you need to see the position of OH groups, whether it is on right hand side or left hand side. OH is on right side of the asymmetric carbon, D configuration. OH is on left side of asymmetric carbon, L configuration. And more than one asymmetric carbon if you have, you need to consider the asymmetric carbon which is far away from the functional group. So that is how we can represent the configuration, that is D and L. We have some limitations for Fischer structure of glucose. If you consider the open structure of glucose, and the glucose does not give the test for Skipp's reagent test. Skipp's reagent test is shown by compounds with aldehyde. Even though the glucose has aldehyde functional group, and it won't give the test for that. That is the one best limitation I can say. Glucose does not give additional product with NaHSO3, sodium bisulfite. And in glucose we have two different forms of glucose in crystal structure form. One is alpha and beta. So there is no explanation for that. So therefore the open chain structure of glucose is not preferred. Instead of that, cyclic structure of glucose is present. And how would be the structure of cyclic structure of glucose? Let me discuss that one. So now here I am going to write the term that is anomers of glucose. Later we will see how actually the cyclic structure of glucose looks like. Anomers of glucose here. So here the structures are very important one. So let me draw the structures along with the explanation. And now I am going to talk about the glucose, and we know the open chain Fischer structure of glucose, and I am going to draw that. So 1, 2, 3, 4, 5, 6. 6 carbons in a straight chain we have, and just to imagine how I explain, at the top we have OH, isn't it? And at the bottom we have CH2H. Numberings are the very important one. Carbon number 1, 2, 3, 4, 5 and 6. And on carbon number 3, H is on right side, OH is on left side, we know, and the remaining configuration are exactly opposite. So this is the simple method I can explain to remember the structure of glucose. So now you tell me what is the name of this compound. So here I am going to write, this is D plus glucose. So now here I am going to write, the name of this compound is D plus glucose. Now I hope you can remember what actually that D and plus stands for. D glucose on a symmetric carbon, OH is on right side. Here carbon number 5 you need to consider. Plus represents this compound rotates plane polarized light towards right side, and that is the glucose. So this is the open chain structure of glucose what we have. So now what happens here, this is not preferred as I said, so cyclic structure is preferred. In that case what happens here, I will consider carbon number 5 which is far away from the functional group, and we have OH. On this oxygen we have 2 lone pairs of electrons. So what happens here, one lone pair of electron is going to attack on this carbon. This is electron rich and this carbon is electron deficient, and if OH is going to be attacked on this carbon, and the pi electrons which are present on carbon double bond oxygen, they are going to shift over here, and what happens here, C plus and O minus you are going to get. O minus, the hydrogen what we have, that is going to join with that. So this is the just adjustment what I am going to make to convert the open chain structure into cyclic structure, or I can say closed structure. So what happens after this? So just observe what happened, and I am going to draw the structure. So again let me draw the 6 carbons, 1, 2, 3, 4, 5 and 6. So now see, the bottom is unchanged, CH2OH. So carbon number 1 and carbon number 5, these two are joined with O. So 1, 2, 3, 4, 5 and 6. Carbon number 1 and carbon number 5, these two are joined with oxygen. You just see, these two are joined with oxygen. So now if there is a shift of pi electrons over oxygen, we have O minus, and hydrogen is going to be joined with that one, you are going to get OH, and we have H on the right side as it is. So this is how the open is converted into close. Okay, and now if you observe, the remaining thing will be same. Carbon number 1, 2, 3, H is on right side, OH is on left side, and remaining thing is exactly the opposite configuration, OH and H here. So here we have OH means, and here we are supposed to write a H here. So this is the one configuration, and what I got by this arrangement or the change what I am going to see in the structure. So now let us assume I can draw double bond O here and single bond H here, and in that case oxygen is going to attack on this carbon, and there will be a shift of pi electrons over here. Okay, or I can say this H and OH that are going to be interchanged. So one more structure we are going to get, and that is plus, and I am going to draw here, just see here, carbon number 1, 2, 3, 4, 5 and 6. At the bottom we have CHOH. So just we are supposed to interchange the configuration at carbon number 1, and here we have OH and here we have H. Carbon number is the important one, so that we can draw the structure in a very correct manner. Carbon number 1 and carbon number 5 we have the oxygen, and on carbon number H or carbon number 3 we have H on the right side and OH on the left side, and remaining will be exactly opposite configuration with compared with carbon number 3. So these two are the structures, I mean closed cycles we are going to get with respect to alpha D glucose here, and these two are isomers I am going to say, because the mirror image we are going to see here. So now what I am going to say here is these two structures what I got, and these two I call it as anomers. So we'll see what actually the anomer word stands for. So now if you observe these two structures, what is the change we are going to observe? Both are cyclic structure only. The change in configuration we are going to observe at carbon number 1. isn't it? At carbon number 1, we have OH is on right side, and in this structure, on carbon number 1, we have OH is on left side. Okay, and since carbon number 1 OH is on right side we have, and carbon number 1 OH is on left side we have, and therefore this structure now I call it as alpha, and this structure I call it as beta. So what is the actual meaning of alpha and beta? Alpha and beta are the anomers. Alpha stands for OH is on right side of anomeric carbon. Carbon number 1 we call it as anomeric carbon. On anomeric carbon, if OH is on right side, we call it as alpha. On anomeric carbon, OH is on left side, we call it as beta. Try to know that one. Anomers are going to differ in the configuration at anomeric carbon only. And now question is this, what actually anomeric carbon stands for? Now you see, in the original structure of D plus glucose, carbon number 1 if you observe, that is actually not asymmetric. We don't have chiral center here. But when we transformed the open chain structure into closed chain, and carbon number 1 is the chiral center, isn't it? So the carbon which is going to generate chiral center during the formation of a cyclic compound, and that carbon we call it as anomeric carbon. Try to know that one. And in glucose, carbon number 1 is anomeric carbon. Remember, anomeric carbon is different for different compounds, whereas in glucose anomeric carbon is carbon number 1 only, because carbon number 1 it was not chiral and now it is the chiral center, or you can say it was prochiral and here it is chiral. So there is generation of chiral center on carbon number 1, and therefore carbon number 1 we call it as anomeric carbon. That is the meaning of anomeric carbon. On anomeric carbon, if we have OH on right side, we call it as alpha. On anomeric carbon, if OH is on left side, and that we call it as beta. Now the complete name is alpha D plus glucose. And what about the name of this one? Beta D plus glucose. So that is actually the formation of two different the crystalline structure alpha and beta, and we don't have explanation of this with the open chain structure of glucose. And remember, and these two we call it as anomers. These two are anomers here. So now for your reference I will write what actually the meaning of alpha. That is nothing but you need to consider on anomeric carbon. On anomeric carbon, in glucose, carbon number 1 is anomeric carbon. On anomeric carbon, OH group is on right hand side, and that we call it as alpha. And if OH group is on left hand side, and that we call it as beta, and alpha and beta are anomers, and anomers are nothing but optical active isomers which differ in the configuration at anomeric carbon. In glucose, anomeric carbon is carbon number 1. You try to know, and this is actually the concepts about anomers, and this is how the structure I am going to draw, that is alpha D plus glucose and beta D plus glucose here. Try to know what is the meaning of alpha. On anomeric carbon, OH is on right side. What is the meaning of D? On asymmetric carbon, OH is on right side. What is the meaning of plus? This compound rotates the plane polarized light towards right side. Similarly, you can explain with respect to beta, D and plus. Remember, glucose is always D plus glucose only, and that I explained how to identify the D, how to identify alpha, and plus and minus, they are experimental quantities, we know that one. So now open chain structure is converted into closed chain structure. So this is the representation how we can represent, but the better way we can represent in cyclic structure, and that kind of structure we call it as Howard structure. The name what we have is Howard structure. So now I am going to explain Howard structure of glucose. Howard structure of glucose. So how we can draw the Howard structure of glucose? Remember, Howard structure, that is the cyclic form of glucose of structure here, and now we know that one glucose exists in two different forms. One is alpha D plus and one is beta D plus. So first I am going to draw the Harvard structure of alpha D plus, and later I am going to draw the Harvard structure of beta D plus here. Okay, so now if you consider glucose, now one can easily say that we have a 6 carbon atoms here, isn't it? So now I am going to consider a cyclic compound with 6 carbon atoms. So see here how I am going to explain here. So just this is cyclic with one oxygen we are supposed to consider, and that is the skeleton of the glucose I am going to consider. So I am going to draw the vertical lines that indicates the bonds, the chemical bonds. Okay, these are the chemical bonds. First you need to draw a skeleton like this, so that it will be easy for us to draw the complete structure. Numbering is very important one, you should not forget that. And now if you observe this structure, this is a basic, and using that I am going to draw here. Okay, and if you consider we have oxygen. Okay, the oxygen atom is in between carbon number 5 and carbon number 1. So you should number this skeleton in such a way that the oxygen should be present between 1 and 5. So here we have oxygen, so 1 and 5 should be present in between 1 and 5. So therefore this is 1, this the dot I can say carbon number 1, and this is carbon number 2, this one, and this is carbon number 3. Okay, and this is carbon number 4, and this is carbon number 5, and 6 will be at the top I can say. So now see, carbon numbering should be start from here, 1, 2, 3, 4, 5, 6, and now oxygen is present in between 1 and 5. So I think oxygen is present between 1 and 5, that is going to satisfy with the structure. Remember that numbering we give for carbons only, not for other elements and compounds. The numbering is for only carbons, and these corners are the positions of carbon. Okay, and of course we have the sixth one, that is above the plane. So now this is a skeleton, and now I am going to draw the complete Harvard structure of glucose. For this one we have to follow one rule, and what is that rule is, you should know the alpha D plus and beta D minus glucose, then it will be easy for us to draw the structure of a glucose. And here I have the structure here, I am going to explain along with that, but you need to remember this kind of structure in your mind, and just by recalling you are supposed to draw the Harvard structure here. And the rule is, the groups which are present on the right side, if you just consider the carbon skeleton excluding the cyclic system, okay, and that I can cite as the Fischer structure, and the groups which are present on the right side, that has to be placed below the plane. Okay, so if you consider that one, so these are nothing but above the plane you can consider, and these are the positions where below the plane I can consider, above the plane and below the plane. I repeat, the groups which are present on right side, that has to be placed below the plane. Opposite, we can remember that the groups which are placed on the left side, that should be placed above the plane. So it is better to remember the one out of these two. The groups which are present on right side of the Fischer structure has to be placed below the plane in Harvard structure. This is the one very simple concept you need to know. Let me repeat that one. If you assume that, and if you compare the Fischer structure and Harvard structure, the groups which are present on the right hand side of Fischer structure has to be placed below the plane in Harvard structure. So now we'll compare that one. Now I am going to draw alpha D plus. I told you the carbon number 1 you observe. So carbon number 1, we have two groups, one is H and OH. So OH is on the right side of the carbon number 1, and I should place OH below the plane in the position of carbon number 1. So where we have carbon number 1, here we have carbon number 1, OH we have right side, I am supposed to place here below the plane. Right. So if OH is below, ultimately one can guess the H will be the above. So this is the reason I told you these positions are nothing but the position of carbon, and these two are the bonds related to that. Now carbon number 1 is over. Move with the second one. Carbon number 2, OH is on right side, therefore OH I should place below and H I should place above. Is that right? Now carbon number 3, H is on right side, therefore H has to be placed below and OH has to be placed above. Carbon number 4, OH is on the right side and OH has to be placed below and H has to be placed above. Carbon number 5, that is going to be linked with oxygen. Carbon number 5 is linked with oxygen. We have two groups, one is H and one is a CH2H. Always the carbon, that is CH2OH, that will be always above the plane and H is below the plane, and that structure we call it as Harvard structure of glucose. And this is cyclic structure, you may remember, and that depends on the position of the OH and H on the carbon. Okay, let me repeat that. First you need to draw a 6-membered compound with oxygen, and the numbering you need to consider, and the groups which are placed right hand side here has to be placed below the group. That is about the structure, we call it as alpha D glucose structure. So now I am going to draw Harvard structure of this. What is that? A beta D plus glucose. Now it will be easy for you. Now what I am going to draw here is, again I am going to draw the 6-membered structure. If you didn't get the first one and if it is as same as the first one, just to see how I am going to draw. So you need to draw a perfect 6-membered ring with oxygen. And next what you have to do, you have to draw the vertical lines which represents the chemical bonds, and you should number in such a way that oxygen should be present in between carbon number 1 and carbon number 5. Therefore numbering starts from here, carbon number 1, carbon number 2, carbon number 3, 4, 5, carbon number 6 will be always above, right? And now just you see the beta D plus glucose, carbon number 1, H is on right side, therefore H has to be placed below and OH has to be placed above, right? Carbon number 2, OH is on right side, therefore OH I place below, H I place above. Carbon number 3, H is on the right side, H I place below, OH I place above. Carbon number 4, OH is on the right side, so OH below, H above. Carbon number 5, we have H and CH2H. CH2OH is always above and H is below to prevent steric hindrance, and that is the structure of what actually the beta D plus glucose, and that structure we call it as Harvard structure. So now the name of these two compounds I am going to write here, and the name of this compound is, I am going to write here alpha D plus glucopyranose. For this one the name is beta D plus glucopyranose. So these two are the names of these two Harvard structure. And then the question arises, why we introduce the word called pyranose? The reason behind that I will tell you. If you consider this is one organic compound, and this is nothing but pyran. Okay, so pyran is nothing but 6-membered organic compound with oxygen. And if you just look over the skeleton of that, and these two are as same as structure of pyran, because of this reason we end the word with what actually the glucopyranose. So alpha D plus glucopyranose and beta D plus glucopyranose, and these two are anomers, I can say, isn't it? And then you may ask me, why these two are anomers? You need to consider anomeric carbon. In glucose the anomeric carbon is carbon number 1. On carbon number 1 the configuration is different. On this carbon, on carbon number 1, OH is below, whereas in this carbon number 1 in the structure, OH is above. Therefore there is change in the configuration at carbon number 1, which is anomeric carbon. Now I can say these two are also anomers here. So if you remember this alpha D plus glucose, it will be easy for you to draw the beta D plus glucose. Why? Because the only change is this one. This OH and H has to be interchanged. You are going to get a beta D plus glucopyranose. In this case also same, both structures are alike, so just we interchanged OH and H and we got what actually beta D plus glucose. So this is the reason why represent alpha and beta, and here also alpha and beta. Remember, alpha and beta are the anomers. And anomers are nothing but the sugars or optical active isomers which differ in the configuration at anomeric carbon, carbon number 1 in glucose, and this is how the open chain structure we have two forms alpha and beta, and that can be written in a very preferred structure, and that we call it as Haber structure. This is how you need to remember that one. And only one rule you just remember, the groups which are present on the right side has to be placed below in the Harvard structure. And if you practice these structures here, and in the examination they ask us to draw the Harvard structure, and we can imagine these structures and we can draw the structures here. Remember, now everything is very simple, but you need to keep in mind what about the configuration at carbon number 1 and carbon number 3 only. Okay, carbon number 1 is that depends on whether that is alpha and beta. Carbon number 3 OH is below, whereas in remaining carbon number 4 and 2 OH will be below itself here, and carbon number 6 is always above the plane you can consider. And that is how the open chain structure can be written in the form of cyclic structure, and that we call it as Harvard structure, and these two are the Harvard structure of glucose. And now we'll see one more monosaccharide, that is fructose. Now we'll see what is the structure of fructose. We'll see Fischer structure of glucose. We'll see Harvard structure of glucose. The formula of fructose we know as same as the glucose, C6H12O6. First we'll see what is the source of fructose. The source of fructose is fruits. Fruits contains fructose, and we can call it as ketohexose. Know that we can call fructose as ketohexose. Do you remember what we named for the glucose in the same manner? Aldohexose. Why glucose is called aldohexose? Because we have aldehyde along with 6 carbon atoms. Therefore, aldohexose. Ketohexose. Hexose, 6 carbon atoms. Ketone functional group we have. And the chemical name of this fructose is lavulose. Lavulose is the chemical name of the fructose. Do you remember the chemical name of glucose? That is dextrose. Glucose chemical name dextrose, whereas fructose chemical name lavulose. I will tell you why we have the names called dextrose and lavulose. Now you know that one. Glucose rotates plane polarized light towards the right side, isn't it? And therefore glucose we call it as dextrose, and lavulose we name, this is the name for the fructose because fructose rotates plane polarized light towards left side, and we should write a minus for the fructose here. This is the fundamental concept what I explain in terms of fructose. And now basic thing you remember for fructose, we have 6 carbon atoms, we have a ketone. Okay, so now see, first I am going to draw open chain structure and anomers, and later Harvard structure I am going to draw. Look over here, this is completely different when compared to the glucose. So now 6 carbons I am going to draw. 1, 2, 3, 4, 5 and 6. Okay, I am talking about fructose. Remember, in glucose what we used to do, top CHO, bottom CH2H, but in fructose top is also CH2OH and bottom is also CH2OH. This is the difference you try to know. And ketone is a functional group, isn't it? So therefore carbon number 2 is the position where we are going to get a ketone. Okay, C double bond O linked with the 2 carbons, therefore this is the ketone functional group. Numbering you need to remember. So 4, 5, 6 carbons we have. And the one more concept is same, carbon number 3, H is on right side, OH is on left side. On carbon number 4, OH and H, and carbon number 5, OH here and H here, and carbon valency 4 has to be satisfied. That is the basic thing. I hope you know that one. And this is the structure of fructose. Remember, 6 carbons we have. Top CH2H, bottom also CH2H, carbon number 2 double bond O, this is the ketone functional group, and carbon number 3, H is on right side, OH is on left side, and remaining 2 are the opposite configuration. And now my question is, this is fructose, we know, isn't it? And I am going to write here, this is fructose. According to experimental quantity, I told you this is a minus, therefore we have the name called levulose, and the minus represents fructose rotates plane polarized light towards left hand side. And my question is whether fructose is D or L. Think over it, whether fructose is D or L. Try to know. DL is different, plus minus is different, alpha beta is different here. DL, capital D, capital L. On asymmetric carbon, OH is on right side D. On asymmetric carbon, OH is on left side L. And here if you consider how many asymmetric carbons are there in fructose, carbon number 1 and 2 are not asymmetric carbon, we know. Carbon number 3 is asymmetric carbon, 4 is asymmetric carbon, 5 is asymmetric carbon, 3 asymmetric carbon we have in case of fructose, and you should consider such asymmetric carbon which is at most distance from the functional group, and this is the functional group. Therefore carbon number 5 is the asymmetric carbon, and on this asymmetric carbon OH is on right side. I hope now you can say this is D configuration, D minus fructose. Okay, so this is actually the Fischer open chain structure of glucose. And I told you that one, we have limitations or drawbacks for the Fischer chain structure, and therefore the most preferred structure is a cyclic, and in that we are going to draw finally the Haber structure of glucose. And similarly the rearrangement takes place between the carbon number 5, and we have function group on carbon number 2. In case of glucose, the functional group was present in carbon number 1, that is aldehyde. Therefore the lone pair of electrons which are present on the oxygen, that has to be attacked on this electron deficient carbon, and what happens here, the pi electrons will shift over this oxygen, we get O minus, the hydrogen is going to be attached with this O. So now I am going to draw the structure. So this is how the rearrangement occurs. Actually this is not required, but for the explanation and for better understanding I am going to draw here. So here what I am supposed to do, I am going to draw 5 carbons, 3, 4, 5, because carbon number 2 and carbon number 5 there is oxygen, isn't it? Carbon number 2 and carbon number 5. So this is carbon number 2, 3, 4, 5 and 6. Isn't it? And there is a carbon between carbon number 2 and carbon number 5. Okay, CH2H is the same, I will keep as it is CH2H. Okay, and now see here, C single bond O minus you get, and you are going to get OH, and we are going to get CH2H. So on carbon number 2, one group is CH2H and one more group is OH. We can represent it in 2 different forms. The one form I am going to write OH here, and one more form I am going to write CH2OH, and this is carbon number 1. See here, carbon number 1, 2, 3, 4, 5, 6. On carbon number 2 we have functional group, that is ketone. Therefore this is carbon number 1, 2, 3, 4, 5. And remaining thing same is same, 1, 2, 3. On carbon number 3, H is on right side, OH is on left side, and similarly this is the opposite case, OH and H, and we have OH here, and this is H I am going to consider. And this is the one form of fructose, and one more form of fructose. I hope you can guess what is the change we have to do. We have to change the configuration at carbon number 2. This we have to interchange, isn't it? So how I am supposed to draw that one? So 5 carbons, 1, 2, 3, 4, 5, and the last carbon is the CH2H, and numbering 2, 3, 4, 5 and 6. There is oxygen between carbon number 2 and 5, and the configuration I am supposed to interchange. OH I will write in the left side, and CH2H I will write in the right side, and this is carbon number 1. On carbon number 3, H is on right side, OH is on left side, and remaining is of the opposite configuration, OH and H. So these two are the almost similar structures what I got with respect to what actually the fructose. And now my question is, out of these two, which one is alpha and which one is beta? Of course these two are anomers. How you said these two are anomers? Because here we have a carbon number 2 and this is the anomeric carbon and the configuration is going to be changed here. Just recall, in case of glucose, which carbon is anomeric carbon? Carbon number 1. Why? Because on carbon number 1, configuration is going to interchange. The change in configuration occurs at carbon number 1. Whereas in case of fructose, the change in configuration occurs at carbon number 2. In case of fructose, the anomeric carbon is carbon number 2. You try to know. So on anomeric carbon, OH is on right side, therefore this is alpha. On anomeric carbon, OH is on left side, therefore this we call it as beta. And the complete name I am going to write, this is alpha D minus fructose. And this is beta D minus fructose. So this is how I am going to draw the anomers of these two, and try to know these two are nothing but the anomers of fructose, anomers of the fructose, and the meaning of alpha and beta is same. On anomeric carbon, OH is on right side, alpha. On anomeric carbon, OH is on left side, beta. In glucose, carbon number 1 is anomeric carbon. In fructose, carbon number 2 is anomeric carbon. So on anomeric carbon, the configuration is going to change. So that is how the open chain structure is going to be converted into cyclic chain. In fructose, carbon number 2 is only the anomeric carbon. Why? If you just see here. In case of Fischer structure, carbon number 2, that is the prochiral, or we don't have asymmetric carbon in that carbon number 2. But after converting into cyclic structure, carbon number 2, we can draw, we have a chiral center here. So carbon number 2 is going to generate a chiral center because of generation of a chiral center at carbon number 2. So carbon number 2 in fructose is anomeric carbon. The configuration is going to differ in that. So now what I am going to do? I am going to draw the most preferred structure, that is the Haworth structure. So Haworth structure of fructose I am going to draw. Of fructose, we know that one fructose exists in a two different form. One is alpha and beta, and now we are going to draw the structures of that one. But just remember, in case of previous glucose, we have a cyclic ring in between carbon number 1 and 5, isn't it? But here we have a cyclic ring in between carbon and 2 and 5. With respect to that, you are supposed to draw the structure here. So now see how I am going to draw the structure with that one. So this is the structure I can draw for the fructose. This is a skeleton, okay, skeleton here. So we have 5-membered cyclic ring with oxygen here. Why 5-membered? Because see, the cyclic we have carbon number 2, 3, 4, 5. We have the 5-membered ring you are supposed to write here. So oxygen is present in between 2 and 5. You should number in such a way that the oxygen should come in between 2 and 5. Therefore, this is carbon number 2, this is carbon number 3, this is 4, and this is 5. The corners indicates the position of carbon, and the vertical lines are nothing but the chemical bonds what I am going to consider here. Okay, and the rule is same. So what the rule we need to follow? The groups which are present on the right side has to be placed below in Haworth structure. So now I am going to draw the alpha D minus fructose, carbon number 2, the right over, carbon number 2, OH is on right side. So therefore I have to place OH below. Left side we have CH2OH. So I am going to write here CH2OH, and this carbon will be carbon number 1. Numbering is for carbon, I told you that one. Carbon number 3, OH is on right side. Carbon number 3, H is below, H is below. okay, and OH is above. Carbon number 4, OH is on right side, therefore OH has to be placed below, H has to be placed above, and CH2OH and H, I told you CH2OH has to be written above the plane, CH2OH, and here is what actually H. There is always a bond between carbon and carbon, and in this case carbon and oxygen only. Don't write any element related to that, and that is the Haber structure of alpha D minus fructose. And now if I ask you to draw the Haber structure of beta D minus, what is the very simple change we are supposed to do? You have to interchange the configuration at carbon number 2, isn't it? So just interchange CH2H and OH, we are going to get that one. So here I am going to explain once again how we can draw the Haber structure of fructose. So first you need to consider the 5-membered cyclic ring along with oxygen, okay, and the vertical lines we have to draw that represents the chemical bonds, and the numbering has to be done. So it starts with 2, 3, 4 and 5, okay, and beta we are going to talk about on carbon number 2, CH2H on the right side, therefore I am supposed to place CH2OH below, and one more is what actually OH above. Just see, that is exactly interchange of that. And carbon number 3, H is on the right side, therefore H I place below, OH I place above. Carbon number 4, OH is on the right side, therefore OH below, H above. Carbon number 5 we have OH and CHO, and here I am supposed to write, what is that, CH2OH, and we have CH here. So these two structures are alike, and the change we are going to see in that carbon number 2, and that carbon is nothing but the anomeric carbon, and observe here we have OH below, here below the plane, and here we have OH above the plane. So remember, these are nothing but the groups which are present above the plane, and these are nothing but the groups which are placed below the plane. The right hand groups has to be placed below the plane here, okay. So these two are nothing but the Haber structure of fructose, and the configuration is going to differ at a carbon number 2, that we call it as anomeric carbon. Now I am going to name these two. So how we are supposed to name that one? This is alpha D minus fructofuranose. See the name, how I named it, alpha D minus fructofuranose. What about this? This is beta D minus, isn't it? Beta D minus fructofuranose. So the change what we are going to observe here is, I introduced the word called furanose. Just recall for the glucose what the word I used, pyranose. Here furanose. Why I used the pyranose? Because the structure is alike, the skeleton is alike as pyran. So furanose, okay, and here I am going to draw the original organic compound, and that is nothing but furan. This is furan is nothing but 5-membered cyclic structure including oxygen, that is furan, and therefore the name what we used, fructofuranose. Alpha D minus fructofuranose, beta D minus fructofuranose, and this is how we can draw the Fischer structure of fructose and anomers of fructose, and the most preferred, most stable structure, that is Haber structure of glucose. So that is all about one more example for monosaccharide that I considered, that is fructose. And now in the next session we'll talk about disaccharides and polysaccharides. Thanks for watching.